Remember the Mineral Springs earthquake? Magnitude maybe 5. Not related to wastewater injection, I don't think. Well, it certainly wasn't. But this is a swimming pool in Virginia, I guess, responding to that. Not super spectacular. Yeah, you can see the swell. Yeah, so just the right resonant frequency of what's going on. So let me stabilize that. Let me oh, that's the more interesting one. Let's not do that. Let's stop that. Running? Yeah, it's running. So this is another larger earthquake in Japan. I guess 8.9, close to 9, which is the magnitude of this the March 2011 East Japan earthquake or Tohoku earthquake. You can see the timing going. It's a swimming pool at some hotel, giving you cues of what to look at. Fluids, of course, so there's some relevance here. We'll talk about the relevance in a little while. So the camera shakes. Camera shakes because it's attached to the ground, clearly. So a big earthquake usually lasts for about a minute and a half. A minute and a half when you're hoping that it's not going to get worse. You're hoping it's going to fade away. But this is the major shaking that comes with it, and I guess, well, you see what you can imagine what's happening. You can see the level of the swimming pool being, the side of it being inundated over the top as you set up this sesh wave that is controlled somehow by the length of the pool because it travels up and down the pool at a certain frequency. In the same way that you pluck a string on a guitar, there's a certain resonant frequency that a pool will have that if you excite it for that given length and depth, then you'll get the highest waves out of it. And so clearly that fits with we could calculate this, I guess, from our knowledge of the wave speed, the celerity wave speed, which is the depth of the pool multiplied by gravity square root. And so you could work that out with the wavelength of the pool to see what the frequency of the shaking was and to see whether it makes sense that it's doing exactly what it's doing. Where is it? So I don't do that. I don't want to do that. Yeah, shout.
That means that ice waves in the pool just after the earthquake. So you can use the pool essentially. Use it as the wave is getting a little bit smaller.
Yeah, I guess there'll be no more input after that. So I guess it will, right? It'll stop. So it has to be within the period of shaking. Cool. This is one of your forerunners brought this to my attention. Kind of a cool video. Watch this. So sitting in a bus. The bus has been sitting out in the rain. It's got a double pane window. Some water's gone between the two panes. And you see that line there, which is the horizontal line. Bus takes off and goes somewhere. What happens to that line? And so the bus is accelerating, going maybe decelerating now. Constant speed, it's flat, but it flips around. And so what we'll talk about today is behaviors as fluids accelerate. It's still fluid statics, but it's talking about fluids which are in a container and therefore aren't circulating along the pipe as we would need to understand to use Bernoulli's equation, but are contained in some fashion such as this. It seems like a trivial example, but I think it's interesting. You notice that it changes from its inclination to being flat and declinates depending on the velocity. If you looked at the relative speed of the bus by the markers outside, you could perhaps correlate that and show that it happens with acceleration, which we'll show today. And there's a corollary between that and this, which I just pulled up. If you drive down by the Nittany Mall today, there's probably 30 of these cars floating around. These have been seen a huge resurgence lately because of the oil boom in the U.S. and in North America in general, carrying tar sands crude across Canada to the East Coast, carrying Bakken oil from the North Dakotas to the East Coast. Not the safest way to transport it, but you'll see in the news now this big furore over indigenous populations in the Dakotas not wanting a pipeline to come through there to take Bakken oil from North Dakota to Illinois. And so despite not being the safest way to transport it, it is the practical way by which most of the liquid hydrocarbons from tight oil are being transported around the country now. It's a problem because they're actually quite volatile. And so they tend to go through cities where all the major rail lines go, just because that's where population is. And sometimes they fall off the tracks and sometimes they explode. I'm not sure, was it a few years ago that Lac Mégantic in Canada was the town where someone parked a trainload of these things outside. The brake mysteriously went off the train in the night. These rolled into town and just decimated the town, killed 40 people or so, maybe a couple of years ago. But there's a linkage between what we just looked at in terms of accelerating fluids and the design of these tanks. If you look at this, this is where you fill it. But if you look at both the back end and the front end, they're butterflied, so they're higher. And so there's a connection between this in that I presume that the reason for this is that when you fill it to the top here, and you have a headspace here. The reason that you want a headspace here, because if you now start moving this train, and what happens to this water level is the same as in the bus, then you'd fill up this headspace, and if the headspace, for instance, is flat, as in actually most of these other tankers that you see are just dead flat, then water level will rise at the back, and it will spurt out of the filling location. And so I presume that the design of this with these front and back ends butterflied are to take care of this acceleration and deceleration. So there's some pragmatic aspect to what we'll talk about today. Okay, so that's what we're going to deal with today. Hopefully these aren't running. It's not. Okay, we'll use that later. All right, so that's what we'll talk about today. Get this going. So that sets the stage, if you like. So we're going to talk about linear and rotational accelerations. So this is kind of still in fluid statics. Maybe it's the barrier between fluid statics and fluid dynamics, which we'll talk about for the rest of the week. But what we've talked about so far, you'll remember this expression here, which if we write it out for the dz component, says something like change in fluid pressures with depth minus unit weight of fluid is equal to density times acceleration in the z direction. So you remember this is three components. You remember these three components basically represent us accommodating F equals ma. And in all the things that we've done, we've basically taken these and put them equal to 0. So today we won't do that. We'll allow those things actually to be finite, and we'd use them to do these two things. We'd like to know two things. One is, what is the change in elevation within that tank as we move, as in the window? And so I can suggest that maybe those tanker cars could take an acceleration of about 1 meter a second before they start overfilling. And so see if you can tell me why that is by the time we get through this today. And the second is, what are the fluid pressures within that tank as you go down through the column now that you're accelerating it? Do they change in some way? And so what we're going to do is we're going to return to these expressions, and use this part, which is the portion which is the acceleration. And instead of just using it to be able to look at the fluid pressures being uniform as you go between two places within a fluid at the same elevation, and using it to say something about how fluid pressures vary within a static fluid when these applied accelerations are zero, we're going to say something about what we expect the slope of that surface to be. And it will turn out to be this. I won't let you off that easy. We'll derive it, but it'll turn out to be this final expression. And so that's where we're going today. Okay? So maybe you've got that. I'll write down exactly what we're talking about. We'll talk about linear accelerations. And answer two questions. One is, what slope of the free surface? And what pressure distribution? What dP dz, I guess, right? What change in pressure with depth? Write it out in English, perhaps. And we'll then talk about rotational accelerations, as you can see above here, right? And answer the same questions. What slope? These questions. And also, what dP dz? Okay, first things first, right? So that's basically our task for today. So, this is basically the idea. We've seen that from the bus video that we think that this is what's happening. If you looked at the background moving, you'd have seen that it responds to an acceleration, not a velocity. All of the things that we're talking about in this class, we've made the case that fluids, waters, are just the same as Newton's law, F equals ma. And so the only time that a force changes in this is if something happens to accelerate it, move it from zero velocity to something else. If I threw this across the room, it would keep on going forever if there wasn't air drag against it and that gravity didn't bring it down. Gravity is the force that acts on it. But water is just exactly the same as a ball. Particle of water or a glob of water is a bit like a ball, and we can treat it in exactly the same way. And you'll recall that the expressions that we developed to be able to describe an accelerating fluid, basically what you'll recall that what we did was we took this little cube and we said that on this cube we can have a fluid pressure acting and a different fluid pressure acting on the other side. We would have the weight of this, and we would have an acceleration acting, say, in the x direction. If this is x, this is y, and this is z. And using this, we derive this expression, which we've just looked at on the previous page. This is how the book looks at it in compact form. We don't really use it that way. This is how we've looked at it in our compact form. But if you're more comfortable writing these out as individual equations, we have three equations. One for behavior in the x direction, one for accelerations resolving forces in the y direction, and one for the z direction, which is vertically, positively upwards. And those are the three expressions we have here. And so those give us now the behaviors where instead of making these terms zero, we're going to allow those to be. And so it would be like running across the floor with a drink in your hand in a cup. Can you stop yourself from spilling back onto you as you run forward with it in front of you? What is the maximum acceleration that you can go through to not allow that? And so the easiest way to look at that is for us to assume, one, that when we move, we get this free surface that forms, and that this free surface looks something like this. The conditions on this surface would be that the pressure, actually the pressure is equal to 0 here, right? P equals 0. It's also equal to 0 here. And so dP, we could choose a length scale along here. I guess we could also say dP dl is equal to 0 because it doesn't change. Or we could just write that dP is equal to 0. As we go along this contour, the pressure doesn't change, and in addition, it happens to be atmospheric at the surface. That's one condition we know. So let's assume that we can accelerate this in the y direction, which is along this direction here, and at the same time have it going up in an elevator. So you can imagine yourself, I suppose, standing in an elevator, not going at constant velocity, but when it starts accelerating initially, when you feel the load in your legs as it accelerates, and then you feel the opposite when it slows down at its destination floor, but also walking across the elevator at some acceleration, ay. If that's the case, then I'm going in the y direction, this is the x direction, and so there is no acceleration in this if I'm only going in this direction. So you can put ax equal to 0, acceleration in the x direction equal to 0, for this particular regime, if you like. And so we can write out these equations. We know this is equal to 0. We know this is not equal to 0, and this is not equal to 0. All we're doing is we're taking these three equations, we're making this 0, and we're keeping the others. We're realizing this is equal to density times gravity, and we're gathering the two terms for that. Okay? So the other thing that we can do is that if we want to write how pressures change on the surface, what we could do is we could say that the change in pressure as we move in the x direction is due to whatever the pressure changes in the x direction, plus the change in pressure in the y direction, plus the change in pressure in the z direction. And because those are all orthogonal to each other, right, one doesn't have any influence on the other. The idea of orthogonality in a mathematical way is that a vector in the x direction has no impact in the y or the z directions because those are orthogonal. And so by doing this, we're not writing the change in pressure is equal to 3 dP, but because these are all independent. What we can do is we could multiply each one of these now, as is done right below it, by 1, and by 1, and by 1. Right? Just a little game we're playing. And if you look at equation 2, it's just written slightly differently, but it's the same as this equation, I guess call it 1b. Maybe. And so what we could do is we have a term that represents how pressure changes in the x direction. We have a term of how pressure changes in the y direction. And likewise in the z direction. And if we substitute those, we get equation 3. That's it. So we've said something about how it changes as we go from one location to another. And now, if I just scoot up here, we made the point already, as we go across this surface, the change in pressure is 0. And so let's put this term here equal to 0. And then let's rearrange for the terms that we want to know. We want to know how the slope of that surface changes as we go horizontally across the liquid. We want to know dz dy, which is by definition this gradient here, right? This is here, this is dy, and this is dz. And so if we arrange equation 3 into those terms, where we know that because we've said there's no acceleration in the x direction, that's our choice, this term 0, this is what we end up with. And so this is saying that the slope of the surface is not a function of velocities, it's a function only of accelerations. This is gravity. This is the acceleration positively upwards in the vertical direction. And this is the acceleration positively to your right, I guess. And so, in other words, if I wanted to know what the change in slope of that surface in the railroad cars is, if I draw the railroad car here, so it's not a railroad car that looks like this, it's a railroad car that has this butterfly portion on the top at both ends. I don't know, but this is maybe 10 to 1, just looking at it, something like that. If I know that this is 1 over 10, this is equal to minus the acceleration in the y direction. What's the acceleration in the z direction? The bus is going horizontally, it's not going up a hill, so z is 0, and then so it's just g. G is about 10 meters per second squared, so this needs to be about 1 meter per second squared to give you this. That was all the calculation was. And so what it does is it tells us exactly what the inclination of this slope would be in a fish tank as you accelerated in a car. That's basically what it is. So it allows us to be able to calculate that. So that was where my little party game of this came from, of thinking about what the design acceleration for this would be so that this fills up this. Of course, if it fills it up and it goes, I mean, the whole idea is this, right? If it starts off level and you accelerate, then it will do this. If you keep on accelerating, it will try to do this. And if it tries to do this, it'll just spurt out the top, by definition, because it'll all get piled up. Obviously, it can't go up here, and so there has to be an excess fluid that pops the lid. Okay? So I think that's kind of a cool demonstration of what's going on. I think that window in the bus is actually really, really great too. We said we want to know two things. One is what the free surface would be. I guess we could figure out exactly what that is as well. The other thing that we also notice is that although we said that dP equals 0, the change in pressure is 0, we didn't say that pressure was actually had to be 0. Certainly the pressure on this upper boundary here is 0 and doesn't change. But on this contour here, the pressure is not 0, but also doesn't change as you go down the same trajectory. So all of these parallel lines would be isobars, same pressures. So the pressure is parallel to the surface, as is suggested by this free expression. And if we wanted to know, for instance, how pressure changed with depth, then this is the expression that we'd use, just as before. And I'll go down. So obviously, if we want to know how pressure changes with depth, that would allow us to calculate it. It's probably written here somewhere. Let me change this for this. So this is the expression we would use. It's similar to what we had before. You remember that what we used before was that the pressure changes with elevation is equal to minus unit weight, which is equal to minus density times gravity, which of course is this first term here. But we've got another term because there's another acceleration. Gravity acts downwards, always in our frame of reference. Positive accelerations in the z directions are upwards. They happen to be the same sign here, but always AZ is positive upwards, always. And so what does that tell you? It tells you that if you're going up to your room after being in the bar in the evening, you just happen to have your drink in your hand, and your hotel room happens to be above the bar, then there has to be a positive acceleration when you first begin. If there's a positive acceleration, then this term here, this would be unit weight. It has to be larger than the unit weight. It's going to be gravity plus whatever your acceleration is. So 9.8 meters per second squared plus whatever the positive acceleration is. And so if you're accelerating upwards, then relative to this free surface, which is if you're traveling horizontally, but let's ignore that for now. Let's just imagine you're going upwards. Then the pressure distribution, instead of being the normal one, which is given by P is equal to gamma Z, it's going to be equal to P is equal to rho Z G plus AZ. This term here. That's all it's saying. And you can get that from that, right? This is the rate of change. You just integrate this in the same way we did, and you get this. So it's saying that instead of just being this product, which would be when the acceleration is 0, which would be this line here, it's going to be different. It's going to be higher. And if you are decelerating when you get to your floor, then to decelerate this would be negative, and it would be this here. What happens if you fall down the elevator shaft? Apart from the obvious, when you have to stop. Your acceleration would be by gravity, downwards. AZ would be minus G. And so G minus G is equal to 0, this term here. And so the fluid pressure distribution in that case would be just weightless, 0. If someone threw you down the elevator shaft, I guess it would be on the other side of this. Okay? So, right. So, that's realized at least a couple of our things that we want to do, right? So, we talked about linear accelerations. What's the slope? This is the slope. Written in terms of x here, it would be accelerating in x in this particular case, but so we know this, and we know this. So those are useful things though. What about rotational accelerations? Actually, I've got some videos. Let's look at the videos quickly. This is this funky video here. Let's see how he does first.
On a planet in a solar-centric system, and going over today's science file. And today's science file, let's say, why don't the planets get pulled directly into the sun? Well, that's a wicked awesome question. Try this! You will need a mug, some ribbon, a plastic tube, and a spool. Start by getting yourself that mug and some ribbon. You're going to tie a few knots around the handle of the mug to secure it in place. Now thread the ribbon through the plastic tube and through the spool as well. Now tie a couple of knots in the ribbon to secure the spool to the ribbon. Now check this out. The mug is definitely heavier than the spool. Now here's what you're going to do. You're going to give the spool a spin, a lot like this. That's so wicked cool!
All right, that's enough. Centripetal force, you've seen it, right? You've seen it in your previous physics classes. Of course, it's the key feature.
Devices in the hydraulic world. In this video, we will have a conceptual overview. At the heart of the system lies the impeller. It has got a series of curved vanes fitted inside shroud plates. The impeller is always immersed in water. When the impeller is made to rotate, it makes the fluid surrounding it also rotate. This imparts centrifugal force to water particles, and the water moves radially out. Since rotational mechanical energy is transferred to the fluid, at discharge sides of impeller, both pressure and kinetic energy of water will rise. At suction side, water is getting displaced, so a negative pressure will be induced at I. Such low pressure helps in sucking fresh water stream into the system again, and this process continues.
Yeah, good. That's not a bad description.
This is the reason why priming is a...
So that's the idea of a centrifugal pump. That's what I'm going to look for now. Let's see if we can do this again. PPP for photo booth. With my passport pictures at the bottom, maybe. So I don't know whether I can do this. So the same idea. So you can imagine taking this tube. It's too long, but imagine putting it in a beaker of water, filling it so it's primed, and then just with it within water, which is my left hand fist here, swinging it so that it spins. So all the water that's in here, it feels this centrifugal force, just like the cup being pulled up by the swinging piece of string with a weight on it, small weight on it, and it wants to shoot out the end. If it shoots out the end, it displaces fluid from the bottom, and therefore it wants to suck fluid from the bottom, it sucks it into it, and that's basically the principle of a centrifugal pump. So that's the basic idea. So we'd like to be able to understand exactly what the working principles are from that, and we don't quite have the background to do that from what we've talked about so far, but we can maybe catch up with it quickly. Where are we? So let's look at rotational accelerations. That's this part here. I don't know why this is here, but let's get rid of that. And so what we could do is we could think of this little, if we remember what we did for the linear system, we had some equation which was basically minus rate of change of pressure with Z minus unit weight is equal to density times acceleration in the Z direction. We said already before today that this is basically equal to sum of forces in the Z direction is equal to mass times acceleration in the Z direction. And we derived it, as you'll recall, from this basic, I guess it's not drawn there, it's drawn here, from this basic idea. Don't need to go back to that. But if we apply that to rotational accelerations, maybe we can draw another little diagram which kind of illustrates the point. We have the Z direction. Instead of the X direction, we have a radial direction. I'm just going to draw a little differential box on the end. Maybe I'll use some different colors because it makes it stand out. And this would be the radial direction. If we draw something around here, this is the theta direction. This is the velocity that it's traveling at, which is v theta. Now I'm going to put some lengths on this. This is going to be dz going upwards, dr going outwards, and d theta going on these different limbs of this block. All right. What else do I need? I could imagine that this is moving at some rotational velocity omega. So omega equals radians per second. And it goes through some angle theta. And the importance about theta is that we're going to spin this thing. And of course the tip is going to be moving at the same speed all the time. You can think of this just being the piece of water that's in this. It's moving at the same rotational velocity around this, but a velocity is both a direction and a speed. The speed is the same with this tip, but its direction is always changing by this amount theta, so it's actually accelerating. It's the definition of an angular acceleration, that it goes through some angle here, which is theta, per unit time, which is the same as it going around here. So instead of pointing always in this direction, it's pointing this direction and then it's slowly moving around. By definition, that's an angular acceleration where the velocity is just equal to the radius times the rotational velocity. So this is the radius to that little packet. All right. So what else? So the other thing that we notice here are the units of this. The units of this are newtons per meter squared, which is pressure, per length, which is a force per unit volume. And so what we could do is we could go back to the case where we're looking previously at linear accelerations. And if you look at rotational accelerations, then Newton's law is that force is equal to mass times v squared over r, v theta squared over radius. So this is the equivalent of F equals ma, but for rotations. This is a velocity as it's going around, and it's given by this term here. So we could convert it into this. So what we could do is we could take this expression. We've noted that this term here is a body force. It's in newtons per meter cubed, a force for every little packet of water that we have. So there's a force that's applied on every single packet of water. What we could do is we could divide this by a volume, V with a line through it. And we could convert that into what we think that is. A mass divided by a volume density. And we could also write this one out as being slightly differently, as this is a force divided by a volume. The volume of this little cube is going to be d theta, dz, d over dr. I've added this mysteriously, but don't worry about it. This is a volume, right? This is the volume of this little thing here. And so this term now is basically, again, color change. What's a force divided by an area? This is this area here. This is just a pressure, force divided by area. So let me cut to the chase. So this allows us to write change in pressure with radius is equal to density times v theta squared over the radius you find yourself. Yeah, and that's it. And if we wanted to, we could substitute in for v theta being equal to the radius of the length of string multiplied by its angular acceleration. So this is kind of a standard result. We could have derived it in a more rigorous way maybe, but we probably don't need to. It's good enough for us. So you'll notice that there's a little bit of a similarity between how pressures change with depth here and this expression here, where this magnitude here is this acceleration. We haven't actually got the unit weight term here. Fine. So that's basically the idea. All I want to get over to you is the fact that all we're doing, as I put it down, is dealing with fluids like this. It's a weight, and it can be applied that way. Yeah. Which TZ? Thank you. Yes. Thank you. Great. It was indeed. So let's go back to this. And so you'll see this. We could. This is it. So how are we going to use this usefully? This is the expression we've just derived. This one here. where we've substituted, I guess, for v theta is equal to r times the angular velocity, radians per second. I guess we should also note maybe that 1 revolution per second is equal to 2 pi radians per second. We have to work in radians here. Revolution per second, RPS, usually lowercase, I guess, right? And so we have, for this little cube, differential cube, we have a behavior in the r direction, which is faced, on the direction of rotation. We have one in the theta direction, which is the direction it's going, you're looking at, and in the z direction, which is vertically upwards. Again, positive vertically upwards. And those are these expressions here. Not derive them, but take them on trust. And so the reason for doing it is to be able to understand, I guess at some level, how centrifugal pumps work. But the other way to look at it, maybe I don't think we'll look necessarily, well, we do. Actually, you'll see some exam questions that really look at this hose behavior. But the other thing we could look at is do exactly the same things that we did for a horizontal, a linear acceleration. The fluid level in the bus as it accelerates down the road. Why does it take a different surface? What's the fluid pressure as we go down from that upper location where we know? And so we can use this in the same way. We think that if we spin something, from looking at fluids going down a drain, which are spinning, but also disappearing, that there's a cone in the middle which is lower and something on the edges which is higher. It's not really a very easy thing for us to do, but I guess if you spun a can very quickly around on its axis, you could imagine that so long as the fluid was dragged with the motion of the can, maybe with baffles in it, it would be thrown out to the side of the can. And in being thrown out to the side of the can, the surface, if there's a free surface there, would rise, just by physically looking at it. And so maybe we can use these expressions to do exactly the same as we did for the linear acceleration case. We have a free surface. What do we know? We know on this free surface that the pressure is 0 here. We know that the pressure is 0 here, if it's atmospheric. We know that as we go across this surface, the change in pressure, irrespective of whether it's 0 or not, or a parallel contour underneath it, that the pressure change, certainly on the surface, is 0. Who knows about underneath it? We can do exactly what we did before. We can write how pressure changes due to the pressure change in the r direction, the pressure change in the theta direction, and the pressure change in the z direction. We can multiply all of these by 1. Radius, the direction, in the direction of travel, theta if you like, and vertically downwards. Instead of thinking of those like that, we can pair it with the actual term we want, with a box here, which we have here, with a box here that we have here, which is 0, makes life easy, and with a box here, which is this. And if we make the substitutions, and we put this equal to 0, as we did before, then we get a bit more complicated expression than before. So equation 1, if you substitute this as 0, you realize this term is 0, we're only left with 2 terms. This term that we just kind of derived, with an analog with F equals ma, this is the term for pressure change with depth, which is unchanged from before. We have a surface which looks like this. We want to know what the surface looks like. This is dz dr, right? If this is the center line, this is the center line that's rotating around. This is the r direction here. This is the z direction here. This is just kind of redrawing this, a little piece of this further down. And so the term we'd like to know, I suppose, is dz/dr, how the surface changes as we go radially outwards. And so we have a dz, we have a dr, we can rearrange them, and we end up with this expression. It changes linearly with radius, so the slope changes linearly with radius. So in other words, if you go twice as far out from an initial point, the slope of that will change to be twice as steep. So it's no longer going to be this linear slope, constant slope that we had before, constant gradient, constant slope. It's going to be curved because it's going to get steeper as we go further out, and we can tell that from this. And if we wanted to be able to see what the slope is, we do what we do normally, is we just integrate it. So rearrange this expression for dz is equal to rho r omega squared over unit weight times dr, which is this. And you integrate it. Integral of this, starting from the center, is just depth. You could put it between limits. Integration of this is a half r squared. And you can either integrate it between z1 and z2 and r1 and r2, or instead you can just do it without limits and just leave the constant. That's what the book does, and that's what we'll do here. And so we know now that the elevation of that surface at any radius is given by this expression, but we don't necessarily know what this is. And so in any problem that we solve, we have to be able to solve first to figure out what the constant is by applying the equation at some known location. Once we know what the constant is, it's constant for all cases in that particular case, and we can solve other expressions. Okay? And so in other words, so I guess this is the standard result here that we'll use. So that gives us the location of the surface. We could also do it for the pressure. We looked before at what the fluid pressures were and how they changed with depth. So if we also went back to this expression here, don't want to give you whiplash, if we go back to this expression here and don't put dp equals 0 and instead go vertically downwards, bless you, then that's this expression here. We integrate with respect to pressure and we get this expression. So the two standard results coming out of here are these two expressions that we have. One says that the surface, as you go further out, it varies with a quadratic, so it's a curvature to it, almost like an arc of a circle. And we could surmise that from the previous figure that we looked at that showed this thing going down the drain that is low in the center and goes out towards the side. And if we go vertically downwards, we have a portion of it which varies with depth, just as before, but the magnitude of the fluid pressure will change as we change the radial location as well. And so we have to be aware of that. Okay. So two standard results. 5 minutes. Let's do a quick example. Very straightforward to be able to look at the case. Okay. Everyone okay with that? So those are the two standard results that you need. So they're kind of identified on this first page as well. I guess this is one. And I suppose the other one would be the bottom equation on this plot here. So that's the second one, and that's the first one. And this is the first one. So how the pressure changes with depth is number 2. What the surface looks like on the surface is number 1. So those are the two standard results that you have. The top one's for linear acceleration, the bottom one for radial acceleration. Okay? All right, just do this quick example. So, interesting idea. So you take a tube, you bend it upwards, you fill it with water, and you spin it. Because, as you remember, if you think about a drum, the water tries to creep up the edges. As you spin it faster, it'll try and creep higher and higher. Ultimately, in the middle, it will actually be dry at some stage, right? You could imagine. So what that's meaning is it's applying tension to the middle. And so in the same way that if I filled this up with water, put my thumb over the end, and I swung it around my head, there'd be a fluid pressure suction on my thumb holding this. If I spun it fast enough, and you could calculate that, then the pressure would get low enough that the water would turn into vapor. It would cavitate or become zero. And so the question is here is how quickly you have to spin this U-tube to be able to make that happen. How do we calculate that? We have a U-tube. We can calculate what the fluid pressure is from this equation. It's the last equation we looked at. We want to know what the pressure is here. This is where the minimum pressure will be as it tries to cavitate. What's the pressure at this? The pressure is equal to either 0 gauge pressure or 14.7, it's in English units, absolute, PSI. Absolute. And so you could work in either. This example chooses to do it in 0 gauge pressure. So we know the pressure here. And so we could write an expression saying the pressure at that location is equal to density, the spin rate, radians per second, the radius, which is 4 inches, squared divided by 2. Its location relative to some datum. Let's take the datum as z equals 0 here. So this location here would be plus 12 inches. This would be 4 inches squared. 4 inches squared. Not meters, inches. And so we know that the pressure here is atmospheric. If we choose gauge, as the question does, then we have everything in this to calculate exactly what the constant is. We can calculate the constant is equal to, actually not a single number here, actually it is a single number, but it's a function of the swing rate. This is the constant, which is equal to this. Don't click those binders yet. If you throw the constant, which we now know, into this expression, we have a new expression. It gives us the pressure at any point is equal to spin rate, density of the fluid, radius at which we find ourselves, and the elevation of that point. We want to know what the pressure is at this point. And so if you put in a value of z is equal to 0, a value of r is equal to 0, and an unknown value of rotation rate, we can calculate the pressure. We want the pressure to be equal to the cavitation pressure. If we know that the vapor pressure of water is equal to 0.26 pounds per square inch absolute, atmospheric pressure is 14.7. That means you have to lower it from 14.7 to 0.26 to get it to vaporize. So 14.7 minus 0.256 is equal to this. This is the pressure you need at that point, at 0.0. If we know that that's this pressure, the only thing we have left to calculate is the spin rate. That's it. So, a little different from some things we've done before, because intrinsically the expression has this constant in it. And we have to figure out exactly what the constant is first. You could integrate it between locations, you know, z1 and z2 and p1 and p2, and you could do that. But it turns out to be easier to do it this way.